So we have to prove that recurrence and transience are class properties. So we'll first show that recurrence is a class property. Suppose I is recurrent and I communicates with J. So we have to show that J is also recurrent. Now to do this, so let's first see that if I is communicating with J, then of course I leads to J and J leads to I both. But since I leads to J, we can get an M, a non-negative integer M, such that Pijn is positive. So in other words, I will lead to J in n steps. That has to be positive for some n. Also, since J leads to I, you can get an integer, non-negative integer M, such that Pjim is positive. So let's take one such integer n and one such integer m. Now use the identity p power m plus n plus k equals p power m times p power k into p power n. If you use this identity, we get that for all non-negative integer k, Pjj of m plus n plus k would look like this double sum. So essentially in m steps from j, you'll go to some state alpha. And then in k steps, you'll go from alpha to some state beta. And in n steps, you'll go from beta to j. Now, of course, alpha and beta are arbitrary states in S, so that this sum is there. This will mean that in m plus n plus k steps, the Markov chain will go from j to j. Now, obviously, this is bounded when we take alpha and beta both to be equal to j. Okay, so this is the one of the terms here is when alpha and beta are both equals j. So this is bounded by the product of these three things. Sorry, what I meant is alpha equals I and beta equals I. So when alpha and beta are both I, so then this is obviously one of the terms, and then this is bigger than or equal to this guy. Now, this just means that this is equals C times Piik, where C is the product of these two probabilities. And note that by the choice of m and n, these two probabilities are actually positive. So the product is also positive. So therefore, what I have shown is that this Pjj, this probability, Pjj of m plus n plus k, has a lower bound, some constant times Piik, where the constant is positive. Not only that the constant is positive, it's very important to note that the constant does not depend on k. It only depends on m and n, but m and n can be chosen once we know what is y and what is j. So there is no dependence on k on this constant c. So what we have shown is that there exists a constant c such that for all integers m and n, and for all, oh sorry, I am in a mistake. So what we have shown is that there exists a positive real number c and two non-negative integers m and n, such that this holds for all non-negative integer k. This is what we have shown. So we have a c and we have mn such that this happens. C may depend on mn actually, but that's beside the point. The point is c does not depend on k. And this is true for every non-negative integer k. Now, how does that help? Now, note that if I is recurrent, then this sum is infinite. Okay. Now, we can use that and this bound here to show that the same sum for j is going to be infinite. And that will show that j is recurrent. So, therefore, the sum, the same kind of sum for J is obviously bounded by if the sum you start from m plus n instead of 0. Okay, this is the lower bound. And this one we already know is bounded by C times that. Okay? So therefore, this sum is bounded by C times that sum. And that sum is infinite because I is recurrent. So therefore, this shows that this particular sum is also infinite. And therefore, this means that J is also recurrent. So therefore, this argument shows that if I is recurrent and I communicates with J, then J is also recurrent, proving that J is a class property. Now we'll have to show that proving that recurrence is a class property. So now we have to show that transience is also a class property, and that's actually just follows from the fact that not recurrence means transience. So let's just write it out. Suppose I is transient and I communicates with J. We have to prove J is transient, but suppose not. Suppose J is not transient. So not transient just means recurrence. So then J would be recurrent. And since communication is a symmetric property, so I communicates with J also is same as J communicates with I. So therefore J communicates with I, and therefore by the previous argument, this will mean that I is also recurrent, which is a contradiction because we started with the assumption that I is transient. So therefore the only possibility is that J has to be transient. J is not transient is obviously leading to a contradiction. So therefore J must be transient. So this shows that transience is also a class property, and this finishes the proof of the theorem.